In the spring of 2015, a NASA spacecraft was closing in on a world nobody had ever seen up close. It was still millions of kilometers out, and the images coming back were little more than a gray smudge, a dim sphere of rock and dust in the asteroid belt between Mars and Jupiter. And then, in the middle of that gray, something appeared that should not have been there. 2 points of light. They were brilliant, sharply defined, and they sat together inside a single crater, staring out of the darkness like a pair of eyes. Everything around them was the color of charcoal. These two spots were blindingly, impossibly bright. As the spacecraft drew closer over the following weeks, the images sharpened, and the lights did not go away. They resolved, they multiplied, and nobody on Earth could explain what they were. For a few months in 2015, those two glowing spots were the most talked about mystery in the solar system. The explanations offered ranged from the reasonable to the absurd. Ice, volcanoes, reflective metal, a settlement? NASA ran a public poll asking people what they thought the lights were, because the honest answer from the scientists was that they did not know either. The world they were staring out from is called Ceres. The spacecraft was called Dawn, and the answer, when it finally arrived, turned out to be far stranger and far more important than the question. Because those two lights were not on the surface of Ceres at all. They came from underneath it. To understand why the lights mattered, we have to understand what Ceres was believed to be and how badly we had underestimated it. Ceres was discovered on the first day of the 19th century, on the 1st of January, 1801, by the Italian astronomer Giuseppe Piazzi. At the time, it was hailed as a discovery of the first order because it sat exactly where a missing planet was expected to be, in the wide, unexplained gap between Mars and Jupiter. For roughly half a century, Ceres was listed in textbooks as a planet, the eighth world of the solar system. Then astronomers began finding others in the same region: Pallas, Juno, Vesta, and eventually thousands more. If Ceres was a planet, then so were all of these, and the tidy solar system began to look absurd. So Ceres was quietly demoted. It became an asteroid, the first and largest of a swarm of rubble. And for the next century and a half, that is how it was treated. A rock. The biggest rock in a belt full of rocks. That reputation is difficult to overstate. The asteroid belt in the popular imagination is a graveyard, a field of dead debris left over from the construction of the planets, dry and airless and finished. Ceres was simply the largest piece of that debris, roughly 940 kilometers across, about a quarter the width of our moon. In 2006, its status changed again. When the International Astronomical Union created the category of dwarf planet, Ceres qualified alongside Pluto. It was massive enough that its own gravity had pulled it into a sphere, which is something the vast majority of asteroids never achieve. So Ceres went from planet to asteroid to dwarf planet without ever moving. Only our understanding of it changed. But before Dawn arrived, that understanding was still built almost entirely on distant telescope observations. We knew its size, its rough shape, and its orbit. We knew it was probably rich in water in some form. Beyond that, Ceres was a blur. Nobody had ever seen a single feature on its surface. The mission that would finally go there was almost never built. Dawn was approved in December 2001 as part of NASA's Discovery program, the agency's line of lower-cost, competitively selected science missions. Its goal was unprecedented. It would not fly past its targets, and it would not orbit one of them. It would orbit two separate worlds, one after the other, on a single flight. No spacecraft in history had ever done that, and there was a straightforward reason why. Entering orbit around a body means matching its speed almost exactly. and leaving that orbit means undoing all of it. With conventional chemical rockets, the fuel required to arrive at one world, stop, then leave again and stop at a second is prohibitive. The tanks would be larger than the spacecraft. For decades, the physics simply forbade it. What made Dawn possible was ion propulsion. Instead of burning fuel in a violent chemical reaction, an ion engine takes xenon gas, strips electrons from the atoms to give them an electrical charge, and uses electric fields to accelerate those charged particles out of the back of the spacecraft. The exhaust is a faint blue glow, and the push it produces is almost imperceptibly gentle. Dawn carried 3 of these thrusters, using only one at a time, and at full power, a single thruster produced 92 millinewtons of thrust. That is roughly the force of a couple of sheets of paper resting on the palm of your hand. But an ion engine can run for years. It sips propellant so efficiently that it can push continuously, day after day, for the better part of a decade. And those tiny forces accumulate into velocity changes that no chemical rocket could ever match. Dawn launched with 425 kilograms of xenon, and that was enough to reach one world, orbit it, break away, cross the belt, and orbit a second. Even with that technology, the project nearly died. The engines caused ongoing technical concern. The launch slipped from 2006 to 2007, and costs climbed from an original estimate of $373 million to $446 million. On the 2nd of March 2006, NASA canceled the mission outright. 25 days later, on the 27th of March, after a review concluded the technical difficulties could be overcome, NASA reversed the decision and reinstated it. Dawn launched from Cape Canaveral on the 27th of September 2007 on a Delta II rocket. It swung past Mars on the 17th of February 2009, borrowing the planet's gravity to bend its course outward. And then it settled into the long, patient, almost silent acceleration that would carry it into the asteroid belt. Dawn arrived at its first target, the asteroid Vesta, on the 16th of July, 2011, and spent 14 months in orbit around it. Vesta and Ceres were chosen together deliberately because they represent 2 opposite outcomes from the same era. Both formed in the same region at the birth of the solar system, and both were on their way to becoming planets before the process stopped. But Vesta formed dry, and Ceres formed with a great deal of water. Studying both with the same set of instruments meant the differences that emerged would be real differences between the worlds, not artifacts of different equipment. What Dawn found at Vesta was a body that had gone much further toward becoming a planet than anyone expected. Vesta has a basaltic crust formed from ancient volcanic activity, and it has survived intact for the entire age of the solar system. Beneath that crust, it is layered, with a mantle and an iron core, exactly as a small planet would be. Its southern hemisphere is dominated by an enormous impact basin, the scar of a collision so violent that it blasted an immense quantity of material off the asteroid entirely. That last detail connects Vesta to Earth in a direct and physical way. A substantial number of the meteorites recovered on our own planet are fragments of Vesta, thrown into space by that impact and eventually falling here. Long before Dawn arrived, pieces of this world were already sitting in museum collections, and one of the mission's objectives was to confirm the link between the rocks in our hands and the world in the belt. On the 5th of September 2012, Dawn shut off its cameras, fired its ion engine, and slowly, over the course of months, spiraled away from Vesta. No spacecraft had ever left orbit around one alien world to go and orbit another. It arrived at Ceres on the 6th of March 2015, which also made it the first spacecraft ever to orbit a dwarf planet, several months before New Horizons reached Pluto. And it was on the approach, in those final weeks, that the lights appeared. The 2 brightest spots sat inside a crater 92 kilometers across, later named Okator. The larger deposit, in the very center of the crater, was named Cerealia Facula. A cluster of smaller ones off to the east became the Venalia Faculae. The word facula simply means a bright area, which is an honest name for something nobody could yet identify. As Dawn dropped into lower and lower orbits over the following years, the picture became stranger rather than simpler. The bright regions were not a smooth coating. They were pits, mounds, fractures, and domes. A landscape that looked as though something had been forced up from below and had frozen where it emerged. And the survey found that Okator was not unique. Across the surface of Ceres, scientists eventually cataloged more than 300 bright patches, almost all of them inside or around craters. Then came the detail that made the mystery genuinely urgent, and it came from something as ordinary as dust. Ceres has no atmosphere, so micrometeorites strike its surface constantly and directly, grinding it down and scattering dark debris. Anything bright sitting on that surface should be steadily buried and darkened over time. The fact that these regions were still brilliantly reflective meant one of two things. Either something was continually cleaning them, or they were young. Not young in the sense that most planetary features are young, meaning hundreds of millions of years. Some of these deposits turned out to be less than 2 million years old, which on a 4.5 billion-year-old world is essentially the present day. Something on Ceres had put fresh material on the surface, in the recent past, on a world that every textbook described as inert. Working out what that material was became the central goal of Dawn's final years. The spacecraft was pushed into orbits far lower than originally planned, dropping at the end of its life to less than 35 kilometers above the surface, closer than the cruising altitude of an airliner over the Earth. And it stared directly down into Okator. The bright material is salt. Specifically, it is sodium carbonate, together with ammonium chloride, a combination that on Earth we would recognize as the residue left behind when salty water evaporates. And salt of that kind does not simply appear on a surface. It has to be deposited by liquid. What Dawn had been photographing was the evidence of brine, salt-enriched water that had risen up through fractures in the crust, spread across the crater floor, and then evaporated away into the vacuum, leaving a brilliant white crust behind. The lights were not a light source at all. They were a stain. The question then became where that water came from, and the answer is what transformed our understanding of Ceres. By measuring tiny variations in the spacecraft's motion, the team mapped the gravity field of the dwarf planet, and through it, the density of the material below the surface. Beneath Okator, they found a region of unusually low density, consistent with a vast reservoir of brine, roughly 40 kilometers beneath the crust and hundreds of kilometers across, on a world only 940 kilometers wide. The impact that carved out Okator around 20 million years ago did two things. It melted a pocket of ice just below the surface, which supplied the bulk of the material at Cerealia Facula, and it fractured the crust deeply enough to open a path to the reservoir far below. The heat from the impact faded within a few million years. The fractures did not. Brine has been percolating up through them ever since. Carol Raymond, the mission's principal investigator, described the finding as confirmation that Ceres is a water-rich world, of the same family as the icy moons of the outer solar system, which is a remarkable thing to say about an object that had spent 2 centuries being classified as a rock. On the surface of Ceres, salts that contain water lose that water quickly. Exposed to vacuum, they dehydrate within a matter of centuries. And yet, when Dawn's instruments examined the bright deposits, the water was still there, locked in the salt. The implication is unavoidable. That liquid did not reach the surface 20 million years ago. On a geological timescale, it arrived essentially yesterday. And the process that carries it up may not have stopped. Material is still moving from the deep interior of Ceres to its surface. There is very probably liquid down there right now, kept from freezing by dissolved salts, which lower the freezing point of water far below zero. Ceres also carries organic compounds on its surface, detected by Dawn in a separate region. Water, salts, organics, and internal activity on a body in the asteroid belt that we had written off entirely. None of this means there is life on Ceres, and nothing Dawn carried could have detected life if there were. But it means the asteroid belt is not the graveyard we assumed. It contains at least one world with a chemistry still in motion, and Ceres is simply the one we happen to look at closely. Dawn's ending was determined not by its ion engines, which still had xenon remaining, but by something far more mundane. To point its solar arrays at the sun for power, and to aim its antenna at the Earth to speak to us, the spacecraft used small hydrazine thrusters. It launched with 45.5 kilograms of hydrazine. Over 11 years, that supply drained away, and there was no possibility of replacing it. On the 31st of October 2018, it ran out. Without the ability to orient itself, Dawn could no longer turn its arrays toward the sun, and it could no longer find the Earth. On the 1st of November 2018, NASA announced the mission was over. There was no dramatic final maneuver and no deliberate destruction. The spacecraft simply stopped answering. And here the story takes a final turn that is difficult to shake. Missions to worlds that might harbor life are normally destroyed at the end, deliberately steered into the atmosphere or the surface of the body they studied, to eliminate any chance of contaminating it. Cassini was flown into Saturn for exactly this reason. But Ceres has organic material and liquid water beneath its crust, which makes it precisely the sort of place planetary protection rules are written to defend. Dawn could not be allowed to fall onto it. So before the fuel ran out, the mission team placed the spacecraft into an orbit calculated to remain stable for decades. It is still there. A silent, powerless spacecraft, circling the world whose secret it uncovered, forbidden from touching it. And it will go on circling long after everyone who built it is gone. What Dawn did was change the category of an entire region of the solar system. It went to look at two rocks, and it came back having found a layered protoplanet with an iron core, and a water-rich world with a reservoir of brine still moving beneath its crust. The two lights that started all of it were never lights. They were the visible mark of a hidden ocean pushing its way to the surface of a world we had dismissed. And there is something worth sitting with in that, because Ceres is one object among more than 1 million in the asteroid belt, and it is the only one we have ever examined from close range. The technology that made it possible has not stopped either. The same ion propulsion that let Dawn orbit 2 worlds is now carrying another NASA spacecraft toward a very different target in that same belt, a metal one, and it will arrive at the end of this decade. As for what else is hiding out there, we have looked closely at exactly one rock in a field of 1 million. That is a story for another day.